So example 1, find a symmetrically distributed interval around the mean that will include 95% of the sample means when x bar is 368, sigma is 15, and n is 25. So x bar is your sample mean, sigma is your population standard deviations, and then n is your sample size. And when we're solving this question, our first step is to draw a diagram so we can visualize what is going on. So in the diagram, what we have is a normal distribution curve, and then we have the mean, 368, that's your sample mean. And in this question, what we're looking for is the symmetrically distributed interval around the mean that will include 95% of the sample means. So when we're looking for an interval, what we're looking for is essentially x1 and x2. x1 is your lower bound, and then x2 is your upper bound. And between x1 and x2, it will contain 95% of the sample mean. So that's why our probability, our area under the curve between x1 and x2 is 95%. So we know that the total area is 100% and 95% is in the middle. So therefore, on the other two sides, we have 5% in total. And because this is symmetric, this is a normal distribution, so this is symmetric. So therefore, we can divide the 5% by 2, and we'll get the 2.5%, so 0.025 on each side. So again, total is 100%, and because we know that 95% is in the middle, so therefore we have 5% on both sides, and because this is symmetric, so we take the 5%, we divide it by 2, then that's why we get 2.5% on each side. So once we know the probability in each of the three regions here, then what we can do is we can use the formula norm.inv to calculate x, because we're looking for x1 and x2, so that's why we're using norm.inv to help us calculate x. And we know how Excel works. Excel only takes the probability to the left of x, so therefore when we calculate x1, the probability that we're going to use is 0.025, because that is the probability to the left of x1, so that's why we use 0.025, and that's what we did here in the formula shown here. And for x2, we're going to use 97.5%. And the reason why we're using 97.5% is that the probability to the left of x2 is 97.5%. We have the 95% plus the 2.5%. We add these two numbers out, we will get the 97.5%. That is the probability to the left of x2. So that's why it is important to draw the diagram so you can understand what the question is asking. Once we understand the diagram, then now we're going to use the norm.inv formula to calculate x1 and x2. And the only thing that is new for this chapter is because since we're dealing with sampling distributions, what we need to calculate is the standard error. What we need to calculate is the adjusted standard deviations. We don't use the population standard deviation, what we use is the adjusted standard deviation. So that's the only thing that is new with sampling distributions. We use the standard error, we use the adjusted standard deviation, and not the population standard deviations. So our standard error or adjusted standard deviation is your sigma divided by square root n. So sigma is 15, n is 25. So 15 divided by square root 25 will give you the 3. So that's our adjusted standard deviation. That's your standard error. And that's what we're going to put into the formula when we're using norm.inv. We use the standard error or the adjusted standard deviations. So x1, what we have is norm.inv. And then open bracket, it will ask you for three variables. The probability is the probability to the left of x1. Second one is your 368, which is your sample mean. Third one is your standard error. Standard error is what we calculated here is 3. That's why we put the 3 here. We put the standard error into the formula because we're dealing with sample distributions. So I'll show you how to do that in Excel right now. So equal norm.inv, open bracket. First variable is your probability to the left of x, so 0.025, comma, then we have the mean is your 368, and then comma, and then your standard deviation, so standard deviation is your adjusted standard deviation or your standard error, which is your 3, and then we close the bracket, and then we're going to get 362.12, and that's your x1. And then we're going to do the same for x2, norm.inv. And as mentioned earlier, our probability to the left of x2 is 97.5%. And how we get the 97.5% is that the probability to the left of x2 is your 95% plus your 2.5%. So we add these two numbers, that is the probability to the left of x2, which is 97.5%. And then your mean is 368, no change there. And then your standard error is 3, so no change there. And when we plug that into Excel, you're going to get 373.88. So I'll show you how to calculate x2 really quickly. So norm.inv, open bracket, 0.975, that's your probability to the left of x2, comma, mean is 368, comma, and then your standard error, which is 3, and then you close the bracket, you're going to get 373.88. So once we calculate x1 and x2, 362 is basically your x1, and then 373 is basically your x2. And basically what margin of error is in this question is basically margin of error is the gap between your mean, which is 368, and your x1, and that is your margin of error. So the difference between 368 and 362, that difference here is your margin of error. So the difference between your lower bound and the mean is your margin of error. And similarly, margin of error is also the upper bound, the difference between the upper bound and your mean. So your 373 minus your 368, that is also your margin of error. So the reason the gap between the lower bound and the mean is the same as the upper bound and the mean, the reason they're the same is because we have a symmetrically distributed interval, because they are symmetric. So therefore, the gap between x1 and the mean and the gap between x2 and the mean are the same. So therefore, when we have two margin of error, when we times the margin of error by 2, what we have is the distance between your lower bound and your upper bound. And that's how we can understand margin of error graphically.